This video is a brief summary of the installation of a solar electric system at Erie Community College's Green Technology Center. Two unique systems were installed. The first system was a 3 kilowatt DC roof-mounted system consisting of 12 Sharp brand 250 watt modules. The output of this 3 kilowatt DC solar array goes to a 4 kilowatt charge controller. The charge controller is connected to a 48 volt 735 amp hour battery bank and an 8 kilowatt Outback radiant inverter. The second array is a 3.06 kilowatt pole mounted AC module system. This array consists of 12 255 watt BenQ solar modules with solar bridge microinverters attached to the back of each module. The two solar arrays' output combined totals 6.06 kilowatts of DC solar electrical energy. Here is the block diagram of the total PV system. We will break up the installation into three parts: the 3 kilowatt DC shed installation, the 3.06 kilowatt AC pole mount installation, and the balance of the system and battery bank in the basement of the Green Technology Center. We will start with the 3 kilowatt DC photovoltaic roof-mounted array. This array consists of 12 250 watt modules divided into 4 strings of 3 modules each. This gives the maximum temperature adjusted voltage to be less than 150 volts. 150 volts is the maximum allowed voltage of the charge controller connected to the array output. These 4 strings are combined in parallel in a DC combiner box on the roof of the shed. The output of the combiner goes to the charge controller about 80 feet away in the basement of the Green Technology Center. The charge controller directs this DC power to the battery bank first. If the batteries don't need charge, the DC power is pushed to the Outback radiant inverter. The inverter converts the DC power to AC power with an efficiency of about 96%. This AC power can then be used by the on-site loads and any excess power pushed out to the grid. Now we'll take a look and see what the install looked like. Before starting the field installation, all the components must be checked. Pre-assembly of hardware is completed on the ground rather than on the roof. Layout of the roof is an important step. Measure rafter locations for rail attachment. Use a chalk line to ensure straight lines for the solar array. After the roof is laid out, the rail roof flashing is installed. One hole is drilled in the rafter for a lag screw that secures the flashing to the roof. These roof flashings are called quick mounts. Quick mounts are 12 by 12 aluminum with a raised attachment block. The quick mount sets under the composite shingle and lines up with the penetration hole. The quick mount is lagged to the roof. The number of quick mount attachments needed depends on the roof structure. This flashed roof system makes a quality install without any leaks. The S bracket is attached to the top of each quick mount block. The rail is cut to size and then snapped into the S bracket for a secure fit. A rail splice is installed at all seams. The rail splice is secured with self-tapping screws. The module string conductor wire runs are secured to the rails before laying the modules. An equipment grounding conductor is run between the rails to the combiner box. The equipment grounding combines with the grounding electrode conductor and connects to earth ground at the main service panel. The 4 module strings and the equipment grounding conductor are tightly bundled and secured to the rails above the roof. A DC string combiner box is mounted at the base of the roof array. The 4 module strings and the equipment grounding conductor land in the combiner. Each string has a 15 amp DC overcurrent protection. The 4 strings DC outputs are combined to one number 2 conductor and pulled 80 feet in a 2-inch PVC underground conduit and land in the charge controller in the basement of the Green Technology Center. The solar modules are now lifted to the roof and connected to the module rails. The panels are secured with mid-clamps that slide onto the rails. The mid-clamps are listed to bond the solar module frame to the rail, so a separate module equipment grounding conductor does not have to be run to the combiner. The second solar array consists of 12 255 watt BenQ AC modules. They are called AC modules because a microinverter is built into the back of the module. This makes the system output AC electricity. The 12 AC modules combine to one series string and are attached to a DPW top-of-pole mount racking system. The top-of-pole mount racking attaches to an adjustable bulkhead on the top of an 8-inch by 20-foot galvanized steel pole. The steel pole is set 8 foot into the ground in a bed of rebar and concrete. The output of the string of 12 AC modules travels 80 feet to the basement of the Green Technology Center on a number 6 THHN conductor. 2 AC disconnects are connected to the output. A fused disconnect outside on the pole and an unfused disconnect in the basement of the Green Technology Center. A kilowatt-hour meter measures the AC energy output of the pole array. A remote-operated circuit breaker is used as a charge control for this AC solar system. If the battery bank voltage exceeds 58 volts, the remote-operated circuit breaker opens so the batteries will not be overcharged. The AC module system output is either directed to the on-site loads or to the Outback Radiant inverter charger. If the batteries need charge, the inverter rectifies the AC energy to DC energy and charges the batteries. If the batteries are charged and the grid is live, the inverter's AC in and AC out are connected through an internal relay. The energy from the AC array is then pushed out to the grid through this AC grid connection. Now, let's look at this pole mount solar installation. The pole foundation is dug to a depth of 8 feet. The foundation was engineered by the pole racking company. The foundation design depends on soil type, wind loads, and size of the array being installed. A rebar cage and sonotube provide the form for the concrete pole foundation. The pole is set inside the rebar cage, leveled and securely braced before pouring the concrete. The electrical conduit is stubbed out through the sonotube against the pole. The conduit will connect to the underground 2-inch existing conduit and carry the array conductors into the basement of the Green Technology Center. Concrete is filled to the top of the sonotube. The excess sonotube is trimmed level to the ground. The foundation is backfilled and cured for 2 weeks before the solar racking is attached to the pole. The tiltable bulkhead slides over the top of the 8-inch pole. The racking center beam is lifted in place and attached to the bulkhead. The bulkhead has 6 angle adjustments. We will keep the angle flat while installing the array. When finished, we will tilt the bulkhead to give the finished array an elevation angle of 30 degrees. Now all the racking cross members are attached. The racking will support a solar array 4 wide and 3 tall in a portrait orientation. The solar modules are lifted on top and secured to the racking. But microinverter cables are not interconnected until the array is complete on the rack. The module frames bond to racking frame with a weave washer. An equipment grounding conductor is connected to each cross rail and to the pole. An 8-foot ground rod is placed in the ground at the base of the pole. The microinverter cables are now connected to complete the array string. The array is one string of 12 AC modules. Extension cables are placed between the rows of adjacent modules. The last cable of the AC module is a transition cable. The transition cable does not have a connector on the end. The transition cable is run to a terminal block inside a weather-tight transition box that is mounted to the rack main beam. The cable is transitioned to THHN number 6 conductor and run through the conduit to the basement of the Green Technology Center. The array is now tilted to 30 degrees. This tilt will provide the best overall production over the year's sun path for our latitude. More production could be achieved if the rack were tilted twice per year. The rack can be easily tilted to 40 degrees in the fall-winter and 20 degrees in the spring-summer to increase production. The last component installed is a fused safety switch. The switch is fused at 15 amps to protect the AC module string. The switch can also be used to shut off the AC array output. This completes both array module installations. The 3000 watt 12 module 4-string DC shed roof mounted system and the 3060 watt 12 module single string AC module tiltable pole system. Now we will continue with the installation of the balance of the system in the basement of the Green Technology Center. The basement of the Green Technology Center is where the balance of the system components are located. The Outback radiant inverter charger, the F80 charge controller, the GSLC 175 AC load center, the 48 volt 735 amp hour battery bank, and the other balance of the system components. The charge controller, inverter, and GSLC load center mount on the wall as a compact unit. The communications components for the Outback system are the hub and the Mate 3. Both of these components also mount to the sides of the GSLC load center. Conduit is installed between the balance of the system components. Existing underground 2-inch PVC conduit carries the array conductors to the basement of the Green Technology Center. The shed array is DC output, so in the basement, these conductors must be installed in metal EMT conduit up to the inverter input. The pole mount array is AC output, so the conductors in the basement from the pole array can be installed in PVC conduit to the GSLC load center. The conductors for the other balance of the system components are also installed in PVC conduit. The GSLC Load Center is the main connection center for both PV arrays. This load center is the location for bus bars and overcurrent protection to the Outback inverter, the charge controller, the battery bank, the backup load center, and the utility grid. All conductors are color-coded for easy identification. The PV arrays and the battery bank can be turned on and off by overcurrent protection devices inside the GSLC Load Center. A dual breaker controls power to the input of the backup load center. Normally, the inverter AC output breaker is on to supply power to the load center. But if the inverter is taken offline, the breaker is switched to bypass and connects to grid power so the backup loads will still operate. The Radiant inverter input directly connects to the GSLC Load Center battery bus bars by metal plates and keyhole connectors on the top of the load center. The inverter connects to the GSLC AC input, AC output, neutral and grounding bus bars by THHN conductors run inside between the components. The hub and the Mate 3 communication devices also connect inside the inverter. The battery rack is heavy duty and lagged to the floor. Each battery weighs 165 pounds. An equipment grounding conductor is also attached to the battery bank rack and connects to the service panel earth ground. The system's battery bank consists of 12-volt 245 amp-hour batteries. The batteries are connected in a series parallel configuration that can provide 48 volts and 730 amp-hours of energy to the inverter if the grid goes down. When the grid is down, the inverter will convert the battery and solar DC energy to AC energy to provide power to the backup load center. The charge controller connects to the battery bank on the bus bars in the GSLC Load Center. Keeping the batteries at a high state of charge is the charge controller's first priority. The charge controller monitors the battery's state of charge and directs PV energy from the shed array to the batteries. If the shed array can't produce enough charge to the batteries, the inverter will rectify AC power to DC power from the grid or from the pole mount array to complete the battery charge. An Outback Flexnet monitor is installed inside the GSLC Load Center and connects to the battery shunts and the Mate 3 communication device. The Flexnet gives an accurate account of the battery bank's state of charge and charging history. The rest of the balance of the system components are disconnects, load centers, and meters. There are 2 AC disconnects that can be used to shut off the output of the system to the grid. The main AC switch, located near the utility meter, disconnects both the wind and the solar power systems from the grid. When this main switch is off, the wind turbine will be shut down and the solar will not feed to the grid. The second AC switch is located outside around the corner from the main switch. This second switch only controls the solar inverter output to the grid. If this switch is off, the solar array will not feed power to the grid. AC disconnects are always wired with the line side towards the utility. When the switch is opened, the solar output to the grid is off, and the fuses on the switch load side can then be changed without live voltage. 8 circuits were removed from the site's existing subpanel and moved to the solar battery backup load center. When grid power is off, the inverter will automatically switch over to battery and solar power to run the backup loads panel. All other load centers in the system will be off, and only the backup load center will operate to a maximum of 50 amps. The only way to totally shut down the solar PV system is to turn off the inverter or open the battery disconnects. A load panel is dedicated to all the Green Technology Center's renewable energy systems. The output of the solar system is fed to a breaker in the renewable energy load panel. All renewables are combined in the load panel, and the output is supply-side tapped to the electric service between the main service center breaker and the utility meter. All the renewable energy produced at the Green Technology Center provides power to the site loads, and excess energy is pushed to the grid. Two kilowatt-hour meters were installed to measure AC energy production. 1 kilowatt-hour meter measures just the production from the pole mount array. The second meter measures the total of both arrays' production that is pushed to the utility grid. The solar PV output is wired to the top line side of each of the meters. The neutral and the grounds are not bonded inside the meters. The neutral and grounds are separated in all system components and only bonded at the main service panel. 2 data loggers were installed that can monitor and store system energy production data. The BenQ data logger monitors and stores energy production data for the AC pole-mounted system. This data logger can be accessed remotely on the internet. The Outback Mate 3 communications device monitors, stores, and programs the Outback system components. The Mate 3 can also be accessed over the ECC web portal. This completes the installation of the 6.06 kilowatt solar electric system with battery backup at Erie Community College's Green Technology Center. This solar electric system is expected to produce 6,600 kilowatt hours of total energy per year and reduce the site's grid electrical usage by about 30%.